Hi guys, this is Miss Thomas. I'm recording from my MYP Algebra 2. Today's topic is going to be normal distribution. Normal distribution is going to be a long one. I'm going to be breaking it up into two parts. The first part is on everything you need to know inside of a classroom. And the second part is I'm not going to pretend you're dumb. I'm not going to pretend you aren't making the connections as we go through this. So we're going to talk about COVID-19 in the second part. I will make sure you can break it up. That way, if you do not want to take part in the COVID-19 discussion, you do not have to. It'll be a very clear transition when we move on. So feel free to pause before we get there if that's not something you're willing to engage with. All right, I also apologize if there's any background noise. They are power washing my condo, so I am hiding in a closet right now. So hopefully it's not too echoey and hopefully it's not too buzzy. But they are doing it from here to the day I am supposed to put this up, so don't really have a choice. Hopefully this works out. All right, so what is normal distribution? What you see on the screen in front of you are all the concepts that are critical to a curve being considered a normal distribution curve. The graph of a normal distribution is a normal curve. It is the same thing we saw with the z-score, that bell-shaped graph. Every normal curve is going to have the following characteristics. The mean, the median, and the mode are all equal. I know, pretty weird, right? Which is why I was saying we can get away with saying average is the same thing as mean here, but be careful with my AP stat guys, because average and mean are technically different things. But for normal distribution and therefore a z-score, the characteristics of the graph make them all equal. It is a bell-shaped symmetric curve around the mean. We went over that last time. That means the mean is the highest point on the bump, and left and right are symmetric. So if you fold the graph along the mean, it winds up playing matchy-matchy. Now the curves, here's some new stuff. The curve will never actually touch the x-axis. The x-axis is kind of like an asymptote. It can get really close, but it's never going to go below the curve. And it does get closer and closer to the x-axis on the extremes. And the total under the curve is equal to 1. If we're talking about percentage, that means 100% of my data is underneath the curve. That's what they're saying right there. All right, brought up percentages. So here we go. The big difference between z-score in normal distribution is z-score pretty much deals with it almost like it's an x-axis. It smushes all this data down to the x-axis and is talking about how far left or how far right you are from that mean. What normal distribution does is it talks about how much data is under the graph at certain locations, and it has to be a range. You can't just say at this exact number. It has to be between these numbers or up to these numbers or from here to here type of thinking. These are the percentages that go along with the data, and they fall into this rule if it's normalized pretty much every single time. I told you that almost everything was right around the middle. Well, it turns out that there's numbers you gotta kind of memorize, the 68, 95, 99, 7 rule. And what that means is that 68% of my data is going to be right here within the +1, -1 range. Okay? If I go out to the +2, -2, I then have 95% of my data is going to be between a -2 and a +2 on the z-score. And between a -3 and a +3, you're going to have 99.7% of your data, which is why I was telling you z-scores are pretty much between a -3 and a +3. Anything exceeding those -3s and those +3s are what you're considered to be an outlier. And notice 0.1% will fall as an outlier on either side. So each section has a percentage. And then you have these ranges that give you a lot of your information. Okay? So basically that's normalized, right? And I know you go, wait, does data really do that in life? Well, here is my cumulative SOL results for the time I've spent at Stonewall Jackson High School. My average SOL score on the Algebra 2 is a 454. Here's my +1, +2, +3 standard deviations, -1, -2, -3. What this is telling me is it falls into this graph every single time. So my data is biased a little bit, and I skew on the higher side of average. If you looked at the state's data, it'd be a much smoother bell curve. Mine is kind of shifted to the right, so my graph, my data is biased in a positive way, which is good for us. It means my test scores are a little too high for what the state would like, which is fine. And it also means that getting a pass is a -1 point something. Getting a 400 with me is not good enough. You're still at a -1 point something. Okay? All right. Is all data capable of being normalized? The answer to that is no. So let's look at this. We've got some math quizzes. So here's my ranges of my scores. Maybe these are in alphabetical order. And no, I'm making it up. This doesn't reflect anything we saw in math class. So just a bunch of numbers, okay? We can put them on our graph. And what we're making here is called a histogram. You might remember that from grade school. You just kind of like stacked things up one on top of each other. So I put an X on the number line every time I hit one of these numbers. So 55 is here, 65, 75. Oh, another 75. So I went up, stuff like that. If we're looking at just the math quizzes, I can, in my mind, see that bell curve. This would be considered normalized. So I have a mean right here. My mean is at 75. And I also have a standard deviation. Now the deviation is how do I go from one chunk of data to the next chunk of data. Notice I've got a big break here. And to go from 75 to 85, I'm adding 10. So my standard deviation is a 10. So there's my -10, so -1, -10, -2, -10, -3. So getting a 45 on this quiz would put you at -3. Anything below a 45, you would be an outlier, okay? When we go in the positive direction, +10, that'd be a +1 deviation. +10, this would be a +2 deviation. There is no +3. And even though this data is normalized and the fact that there's no +3, that's fine. That's why your data is going to look closer to this sometimes with testing, is because there is an upper limit. You really can't go above 100, so the data kind of hits the ceiling and everything. Like if you can picture people running and smacking in a wall and just kind of stopping and building up there, that kind of happens anytime there's a ceiling on your data. Here we go, not normalized. Like the amount of money you can make on a paycheck. You have a part-time job, somebody makes 500, another person makes 300, all depending on how many hours you get. And when I put that data up, it looks like this. There's no bell curve here, so this is not normalized data. Maybe if we took it across the entire country of paychecks for teens 15 through 19, we might get normalized data, but with the data I have right here, it's not. So we would not do any normal distribution analysis on data that look like this. Okay, so let's get to work on doing some statistical analysis with the normal distribution. All right, the following graph represents the height of American min, where the height of American min approximates the normal curve. That phrase is always going to be there. That basically says you can do work here. The mean is 70 and a standard deviation of 3. So if you are 70 inches tall, then you are taller than what percent of the population? So I have my bell graph, I have my normal curve, and I marked my mean of 70. It's right smack in the middle. I'm going to use this blue square to go underneath it to kind of show you the area I'm talking about. It is not going to match perfectly. Realize I'm talking about under the curve, so visualize it and pretend a little bit as we go. So if you are 70 inches tall, I am talking about this part of the graph that's now in blue, up to there. Remember we talked about this being the halfway point, and it was symmetric. So half my data is this way, half my data is this way. That means my 70 at my mean is at the 50% line. So 50% of my data is right there at my mean. So if you are 70 inches tall, do the math on that one, not quite 6 foot, not quite, okay? You are 50% taller than half the population of American men. All right, if you are 64 inches tall, all right, 5'4" guys, then you are shorter than what percentage of the population? All right, so we need to figure out where 64 is. Yes, this is 70. All right, and gotta go here, so this is -3 because of the standard deviation, so this is a 67. And then I've got to go, we'll adjust, -3 is 64. And we'll move things around, see how I got with. Okay, close enough. Maybe a little bit more. And we'll shift. Okay, so here's my 64. So 64 is shorter than what percent? That means I'm looking at everything to the right. I'm gonna have to make my little blue guy, whoop, wrong thing. My blue guy is gonna have to be a little bit bigger for this. Wheel now. Okay, so I'm talking about everything this way, all these percentages. So we're going to go back to my percentage slide and we're going to look at it. This is my mean, this is a -1, this is a -2. So everything to the right of -2. So here's a -2. So I could say this plus this plus this plus this plus this plus this. Or, knowing it's 100%, I could do 100% minus 2.1 and minus 0.1. So this equals 100 minus 2.1 minus 0.1, which is the same thing as 98.8. So if you are 5'4" as the guy, you are shorter than 98.8% of the population. Okay, so the next one, if you are 76 inches tall, so that's going to be somewhere over here. So I need to extend my graph. So this would be 73. This would be, let's see if I can. Where am I? Come on back. Here's 76, and here would be 79, okay? So if we are taller than 76%, so I'm going to move this in. This time we're talking about everything to the left of my number, so that way would be shorter. You are taller than what percentage? So again, I could do the same thing and take the 0.1, 2.1, 13.6, 34.1, 34.1, 13.6, and add them up. Or I could do the 100 minus. And either way, I'm at a standard deviation of 2. Whoops, the answer is the same. 98.8%. You are taller. So if you are 6'4", you are taller than 98.8%. I'm sorry, wait, hold on. Is my math wrong? Yes, it is. 97. Ha ha ha. Everybody makes mistakes. 97. Okay, so here's an interesting one. What percentage, oh, it's going to make me move everything, isn't it? Okay, what percentage of men are between 61 and 73? So we don't have 61 on the board, so I'm going to go and, yeah, we're going to, whoa, wrong way. I'm gonna try and space these out. And shift it. So that, there we go, 61. So we're looking between 61 and 73. So 61 is here. I'm gonna have to shift. Oh, look, it worked, nice. So this time I'm talking between my 61 and my 73. So between my -3 and my +1. So going back here so you can see those numbers again. 2.1, 13.6, 34.1, and 34.1. So to find this percentage, and because I'm in my closet, I don't have everything, this is going to equal 2.1 plus 13.6 plus 34.1 plus 34.1. 2.1, 13.6, 34.1, 34.1, and whatever that winds up being, somewhere around, 68, around 80%, give or take. You can add those up. This is what the percent would equal to, okay? All right, so here we go again, this time with SATs, and don't worry, you'll get a chance to call me short in a minute or two. Following graph represents a graph of the SAT math scores over the last 20 years, where the SAT scores approximate the normal curve with a mean of 510 and a standard deviation of 95. If you scored a 605 or higher, how did you score in comparison to the whole group? All right, so 605 or higher. This part, okay? Right, we're talking about this part. This time I have the mean and all the deviation work done. So now we're talking about this. So we are talking about these percentages. So this was a 13.6, this is a 2.1, this is a 0.1. So to find this answer, I've got to move this then. This is going to equal 13.6 plus 2.1 plus 0.1, right? And we're going to get that as a percentage. So that is 15.8%. Okay, so you're in the top, basically the top 15%, if you can score a 605 or higher on the math. If you scored above a 700, what percentage are you in? So now we're over here, 700, okay, so just that section. So this one, which is a 2.1, and this one, which is a 0.1. So this would be equal to 2.1 plus 0.1, which is going to be 2.2%. So if you can score above a 700, you are in the top 2.2% of SAT scores. If we go to the 415, we're down here. So below a 415, again, this is 13.6 over here, and 2.1 over here, and 0.1 over here. So if we go to the 415, so if you score below a 415, you are in the 15.8 percentile. Okay? You could also say for this one that you are in the top 85%, and we'll go over that again. Wording is subjective. As you can start to see, higher, lower, above, below, those are kind of keywords that you need to be paying attention to as you do it. And then when you go to phrase your answers, you want to make sure you're reflecting the same wording. So notice I would say here, I'm in the top 15.8% since I'm talking about this, right? And for the 415, I would say I'm in the bottom 15.8%. And you need to use the qualifier when you go to talk, because the numbers are going to be repetitive like that. You need to say where it is. Is it the top? Is it the bottom? Okay. You could, for this one, also say I'm above 84.2%. So what percent scored between a 557 and a 725? And that's a little bit weird, right? Because I don't have those numbers as standard deviations. So here, well, not even that, even tighter than that, okay. Right? Here-ish. And I don't have those deviations. Remember, we ran into the same problem with the z-score, and we had to actually use the formula instead of the deviation marks to figure it out. Same thing happens with the normal curve. When you wind up with numbers that don't match a mean or a deviation, that's where we're going to turn to our calculator and we're going to use our calculator to do the deviation figuration for me. What you see on the screen in front of you is the calculator button sequence you need to hit in order. Go ahead and pause that screen and play with it. This is me working through that last problem, okay? So we're going to start with hitting the blue button, the second function button, and this variables button right there. If you notice, the word in blue looks like distribution, the start of distribution. What you're doing is distribution. That's why we're picking it. From here, you have two options that have the word normal. You're going to take normal CDF. No, I have no idea why. We just got to get over it. And that will take you to a screen like this where your numbers for lower, upper, mean, and deviation need to be entered. So we're going to take our lower limit, and I'm going to flick it back so you can see why 557 is lower. 557 would have been right here. It's on my far left. My far left is lower. 725 would be over here on the right. Your right is going to be upper. So back here in my lower, I hit the lower of the two numbers I'm checking the range on. I put my 725 in my upper. My mean was 510. That was given to me in the problem. My standard deviation is 95, also given into the problem. And then you're going to hit the word paste. That's going to bring you back to your main calculator screen where it looks like this, and the first time you do it, you go, oh, I messed up because it didn't give you an answer. You just need to hit enter again. Now your screen is going to look like the top line here and have 0.295, blah, 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 blah. All right, this is where you need to adjust your answer off of what the question is asking you. It's asking me for a percentage. So to convert a decimal to a percentage, I multiply by 100. And I would tell me 28 point, however much you want to round it to, 0.9 if we're going to round to one place, 0.86 if you're going to round to two decimal places. Sometimes they'll tell you generally one decimal place is good enough for distribution. All right, so here's where you get to call me short. I am all 5'2.5". So here we go. The height of American women from 18 to 24 is approximately a normal curve. Mean is 65.5. Standard deviation is 2.5. This is two questions. So the first one we're going to answer is if you are between 60 and 61 inches. So 5 foot and 5'1". Right? What's the probability I'm going to find an American woman between 5 foot and 5'1"? And then what percentage of women are taller than 64? Basically, both questions are asking you for a percentage that occurs within this range. So here is 60 and 61. 60 is my lower, it's the smaller, so this is going to go in your lower. So you're going to start this calculator sequence again. 60 is going to go in your lower. 61 is going to go up in your upper. Right in the problem tells me mean is 65.5. Standard deviation is 2.5. And after I hit that paste button, it'll bring me back to a screen that looks like this. We look at this number and go, wait, what do I need? I need probability, which is the same thing as percentage for distribution problems. I'm going to multiply this by 100. So the probability I can find an American woman between 18 and 24 who is between 6 foot or 5 foot and 5'1" is 2.2%. Not that many super short people. Okay. What about taller than 64 inches? Well, 64 is my lower bound. I'm going to go back to this graph so you can see what I'm talking about. And when we were doing, higher than 605, right? We were here. Here was my lower number, and I only needed to figure it out with percentages, and I didn't care what this meant, right? Because I could use the percentages. Well, for this problem, I kind of can't. I need to know what the upper bound is, since 64 isn't going to hit nice on my chart if I try to do a deviation. Okay, so going back here, this would be my lower bound, and whatever the heck positive infinity would be, that would be my upper bound. Same thing if I went the other way. This would be an upper bound, and negative infinity would be my lower bound. So over here, I'm looking for taller than 64. 64 is your lower bound, and my upper bound is infinity. Now, how your calculator wants you to write infinity is like this: 1e99 for positive infinity, and negative 1e99 for negative infinity. And the e I'm talking about is the blue E over your division sign. So you're going to have to hit second and the blue button to get the E into your calculator screen. So here we go. We're going to walk it through. You're going to hit the second variable button. You're going to hit option 2. In lower, you're going to put 64. In upper, you're going to hit the 1, the blue button and the division sign to get my E, a 9. In mean, should still be 65.5. In standard deviation is going to be the 2.5. I'm going to hit paste. Brings me back to my screen where I hit enter. I adjust that number for percentage, so multiply by 100. And you should be able to have a number that rounds to 72.6%. And so I am not quite this tall. So yes, about 75-80% of the American population of women are taller than me. Told you you'd have a chance to make fun of me in a moment. All right, calculus exam, since that's where we're going next here, folks. Calculus exam is given to 500 students. The scores have a normal distribution with a mean of 78 and a standard deviation of 5. So I'm asking going to do the same setup, but 2 different types of answers, right? So let's pretend that it said what percentage of students scored between an 82 and a 90. Again, the word percentage means I do exactly what I want. Go into that distribution, find normal deviation, or normal CDF, right? Enter 82 is lower, 90 is upper, enter my mean of 78, and my deviation of 5, hit paste, hit enter. Percentage means multiply by 100. And if you've done those button sequences right, you've got 20.37. This time I went to 2 decimal places just to mix it up, right? So about 20% of the students taking this exam scored in the mid to upper B range. Now I'm going to change something. And notice I changed what percentage to how many. How many means I'm talking about number of students. I'm not talking about what percentage, but the physical number of test takers who were in this range. I would start the problem off exactly the same with normal CDF and the upper lower mean deviation and paste enter. But when I get to that step where I have to adjust my answer step 5, I would not be multiplying by 100. 100 gets me to a percentage, and this time I have 500 kids taking it. So I need, for how many, I need to take my answer times how many are taking it. So 500 times the 0.2037, or whatever the number is on your screen, multiply it out, and I get 101.85. Now here's the thing, people. With people, there is no such thing as a fraction of a person. Right? I know, sounds silly, but yet most of you are going to want to write 101.85 and be done with it. How exactly do I have 0.85 of a person? Did you go to school, magically lose an arm, and get sent home on the bus anyway? Mom's okay with that? Yeah, probably not, right? So anytime you are dealing with how many, the longer you can make this, the better the answer you're going to get, because you are going to have to round and make it make sense. I don't have 0.85 of a person. I have 102 people. All right, so here is a few more problems that kind of go through all the different ways problems can be presented to you, right? So I'm going to give you a chance to look at it. I'm going to give you a couple little hints as you go along, so that you can be double checking your calculator screen. That's the beauty and the curse normal distribution, I can't really show you work since it's button pushing. All right, so find the probability of scoring below, all right, a 1400 on the SAT. If the scores are distributed, here's my mean of 15, standard deviation of 2. So mean and deviation are good. It's 1400. I only have one number. Below means my 1400 is my upper bound, and my lower bound is then a negative infinity. So that means when I'm in my screen, negative 1E99 is my lower, 1400 is my upper, 1500 is my mean, standard deviation is 200. I hit paste, I hit enter. It says find probability, so probability is the same thing as percentage, multiply it by 100, and I should be getting a number that rounds to 30.9%. All right, next problem. Normal distributed set has a mean of 0, standard deviation of 0.5. What is the expected values between -1 and +1? This time we do not need a calculator. I'm going to go back to a graph. This one. Here's my mean of 0. This is -1. This is -0.5. I'm sorry. This is -1. +0.5. +1. So I'm within 2 deviations. By my rule, then, I'm at 95%. Could I, in theory, have said lower is -1, upper is +1, mean is 0, deviation is 0.5, and use my calculator? Sure, absolutely could have. But sometimes they take a calculator away from you. Welcome to IB world. You should know that already. So you still need to know those percentages even though I taught you a calculator, which is why I'm showing it to you here. All right, here we go. Normal distributed set of 968 values. It's got that mean, it's got that standard deviation. What's the number closest to it? All right, number closest to be expected above 125. How many values are above 125? All right, above 125. 125 is your lower bound. That means positive infinity is my upper bound. So that would be a 1E99. Enter my mean of 108, my deviation of 11. Paste, enter. All right. That number is not going to get to 59 pretty quick because I'm not multiplying by 100, right? What is the closest number of values? That's the same way of saying how many. Multiply it by 968. But what if they give you a percentage in it? And when they give you a percentage and they ask for a score, you're basically going backwards, okay? So scores on an SAT form a normal distribution with a mean of 500 and a standard deviation of 100. What is the minimum score needed to be in the top 15%? All right, so if we look at my graph, top 15% would be this way. That means the bottom 85% would be that way to your left. All right, if you remember the second function variables in the distribution list on the TA, there were a bunch of options. If you look at option number 3, invert normal, which is basically invert, flip it upside down, and that's kind of what you're doing with the problem, a little shortcut to remember it. Like we normally go from here to here, right, from graph to percentage, but this time we're going from percentage to graph, so we're kind of going backwards, or inverting. So invert normal. The first thing it shows up is area. All right. Area, when they ask for it, is everything to the left. They fill in the graph this way with the blue lines when they're talking area. So if I'm giving you top 15% and we're stopping over here, we've filled from negative infinity all the way up to top 15%. In other words, we filled in 85% of our graph. If you remember, your calculator didn't give you percentage, it gave you decimals. So when you're going to your calculator, you need to give it the decimal. 85% would be the same thing as 0.85. Mean, standard deviation come from the problem. Hit paste or enter. right? Again, rounding to a number that makes some sense, 604 or higher is what you would need in order to be in the top 15% on this SAT. All right, from here to the end, we're going to talk about COVID-19. So if this is not something you want to do, feel free to end the slide now. Good luck on my worksheet. All right, my goal here is not to give you my opinion on COVID-19 and whether you should be wearing a mask or not. That is between you and your parents. My goal here is to make you literate when you are looking at these graphs. In other words, I want you to understand what's going on, and I want you to formulate your own opinion. All right, first thing you need to know when you are looking at any of these graphs, what you are looking at is something called data visualization. And I will tell you right off the bat, if you ever take a data visualization course, it's pretty cool, especially if you like making graphs because it's all you do. But the first sentence out of your instructor's mouth is going to be, data visualization is not about the math, it's about the story. So that's what you need to realize right off the bat. Every time you're looking at a COVID-19 graph, they are trying to tell you a story, which means they are taking this and they're presenting the part of the story that they would like you to hear. Statistics is both beautiful and a curse in that way, in that you can use it to tell your story. And picking and choosing and presentation lets you tell a story. So if we take a look at my top graph, where I've got 4 cities and I've got their average temperatures and I've charted them out over a course of the year, it's basically a hot mess, right? Mathematically, it makes real good sense. It's a line graph. I can see what's going on. Manassas gets hotter here and colder there, and this orange guy is pretty flat, and whoa, the gray one's a little weird, and what's going on with the yellow one? It's backwards from Manassas, okay, right? But most people are going to look at this and go, I don't understand. But this is a presentation of the math, right? This second graph down here is the exact same math, but I presented it in a way to tell a story. I've picked colors that tell a story, that highlight what I want you to get quick and easy without talking math. So if we look at down here, red means hot, blue means cold. Whoa, dude, Manassas is really hot in July, and Sydney's kind of hot in January and December, right? Pretty much it becomes, the story becomes more focused, okay? So they are telling you stories when they're giving you graphs. All right, step it up a little bit in terms of knowledge. There are 2 ways you are going to see COVID-19 graphs, single graphs presented to you. One is going to have a linear scale. One is going to have a logarithmic scale. This is why Democrats and Republicans can both be telling you totally different stories, yet citing the same source. They're picking different scaled graphs. Are there points to both graphs? Yes. Are both graphs telling you the same story? Well, they're both telling you the same math, but looking at them, they tell you a different story. Okay. Linear, here's my numbers, okay, shows this, we're going up. And logarithmic here kind of looks like we might be flattening, right? All right. Linear pretty much tells you and answers the question of how many, okay? And a logarithmic scale should not be alone. A logarithmic scale is designed to do comparison data. Basically, what a logarithmic is saying is some of our numbers are way too big, right? We can't really put them effectively on the same graph here, right? Like 1,000 over here would be like, woo, way over here. And all of a sudden this number becomes really ineffective. And if I kept going, most of these numbers will become really ineffective. where a logarithmic graph is trying to make this number down here as effective, as important as this number over here. Logarithmic graphs are really good for talking about rate of change, how quickly, how long, and a linear graph is much better at talking about how many. Okay, so here is a site that we're going to go to. I have it saved, okay, and we're going to go to it next. Before I go to this site, I want you to think about these two questions. What purpose would Johns Hopkins University have for collecting data? And what story would they want to tell? All right, so here we are, as soon as it loads. Okay, here is the US map, right? Oh, of course, now it goes away. Welcome to my internet. This is why I can't really have live screens with you guys. All right, so we saw it briefly. So Johns Hopkins University, it's a medical center, it's a hospital. The story they're going to want to basically be doing and dealing with is how do I keep people from being sick? In other words, they're going to basically be trying to tell you, you don't want to be here. Here is bad. So they're going to put visual images up. Of course it's not freaking working. Are you kidding me? Oh, here it comes. Right? They're going to be using colors, and they're going to be talking about things that basically in your mind make you go, whoa, I don't want to be there. Okay? So as we're looking, wow, that don't look so good. That don't look so good. Holy moly, that don't look so good. Yeah, but if I had picked all shades of green, would you really be thinking that? No. So they pick red intentionally? Yes. Does that change the math? No. Does it give you a different impression of it though? Probably. Okay? But feel free to go here and play, because they got some cool interactive maps. And here is a world map. Okay? Now I'm going to leave it alone and just let it load and hope for the best with my internet. Oh, here it goes. Yay. Woo. Maybe. Too much data for my computer. Welcome to virtual learning, folks. Alright, but I hope you're in your mind going, oh, look at the red, right? See the beat red. Yeah, that's a lot of people. But that's what they want you to be thinking. That is a lot of people. What do you think when this loads? And you might have to go look at it on your own. What color do you think you're going to see on the world map? Right? Are they, oh yeah, look at that. Okay. Are they telling you a story, right? Red is bad. And for these guys, these are called bubble graphs. The bigger the bubble, the bigger the population, the bigger the test. So this big bubble right here has a lot of confirmed cases, and this little bubble, not so much. Okay? Stories. These graphs tell you stories. Make sure you know the story behind the site before you start citing it as a source. Okay. They even go into linear versus logs, okay, on the site so that you can use both of them. And they do this in the how is the outbreak going section. All right, things to think about here. Why would somebody want to look at a linear? Why would somebody want to look at a log, right? What would it tell us? A linear would basically be telling us cumulative. How many total cases do we have? And a log is going to help you put it into comparison to another country. Another thing to be thinking about when you're looking at any site is whether they're controlling for population size. If I've got 100 people and I have 80 of them who are effective, that's a large percentage. But if I've got 2,000 people and I have 100 people, yeah, I've got 2,000. That's got more cases. But does it really when we're talking percentages? Population size needs to come into play somehow if you're going to compare apples to apples and not apples to oranges. Hey, that's a hint on where we're going with z-score eventually, okay? But think of it in terms of population size as well. So we're going to wait for it to load. This one should load a little easier. The graphs aren't quite as intensive. All right, cumulative cases. And here we go. This is confirmed, right? And if we look at it in terms of linear, US not doing so good, right? Look at how far out we are in terms of total cases. This is how many cases we have. That is a lot. Oh, and it's going up as I put it. That's a little scary. Sorry about that. All right, as soon as I change to logarithmic and watch my scale, see the drop in scale, right? Now we're talking about the rate of change, and notice that everybody's looking at a very similar rate of change. That puts it more in comparison to somebody else. If these graphs were by themselves, though, this one would make sense for a single graph. We have a lot more cases than Ireland. But if we talk about how quickly we are getting new cases, we don't have, yeah, we're still getting a little quicker than, but we're not like, whoa, so far ahead of Ireland with a rate of change. That would be the point between these two graphs. Make sure you understand that before you think about things. Okay? All right. What does flatten the curve really mean? All right. As you should have picked up on by now, almost all the data for COVID-19 is forming into a normalized curve. Thus the word curve. What they're really trying to do is flatten the normal curve. We talked about changing the y-axis with our linear and logarithmic scale. Flatten the curve talks to you about flattening or altering the x-axis. In other words, we're going to take our standard deviations and make them way farther apart. I kind of hinted at that in z-score when we talked about the test average being a 70, and you could have 30 points going to 100, so I could kind of spread out my standard deviations. But when I changed the average to an 88, I only had 12, and so my deviations were really tight. Flattening the curve is taking those tight deviations and spreading them out into wide deviations. So we've got this red line here that we need to be under. Some places will show you that as the number of hospital beds. So we're going to roll with that so that it kind of makes sense. And this would be our data if we did nothing, right? We've got the normal curve and we've got this danger zone up here, so to say, because our normal distribution is very tall and narrow because our deviations are really close. We got it over quick, but we hit the danger zone and lots of people don't want to be in the danger zone, so we need to flatten the curve. Well, if I take this chart and I try to push it down this way, I can do it in this world, but you can't do it in the real world because the moment I go and I push it down, I have to push it out as well. It has to be 100% underneath, so each one of these people can't become a half a person. So I need to make it wider as well. So by pushing down this peak, I'm pulling out the sides and I'm making this graph from tall and narrow to short and wide, which means time-wise it takes longer, but we don't ever hit into that danger zone. And ultimately that would mean less deaths, which is why you're hearing flatten the curve as such an important thing. This is what they're really talking about. All right, so here we go. I thought this was kind of cool. These are graphs of countries that are quote unquote done, because if you look at some of them, you can clearly tell not done. Most of them kind of make it a pretty good approximate for a normal curve. Do not know what's going on here. Something screwy that you know the reporting was not quite right. That's a little alarming for that country. Same with that and that, right? That's why I'm saying done in quotes. But if you look at most of them, that one and this one, you can see it. There's your peak, there's your normal curve, and since these are all on the same x scale, basically they've tightened it to make my x-axis comparable for each one. All right, counting for population. All right, so here we go. We're going to go to Prince William County's graphs now, and we're going to talk about the normal curve for us. Hopefully it's loaded. All right, so here, oh, and this I wanted to show you too, because we were talking about population. Cool. So here we look at this one, we look at this map, and remember they're telling you a story, and this is a story of don't go here, basically. How bad is it here? And look, I've got counts. And if I look at counts, whoa, 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 right? Look at this if I change it in an account for population. Hopefully it loads, because this is really cool. Woo, there, that was quick. Okay, look at how the colors start to even out. So other than a couple places over here, Virginia's doing about the same per population. And when we go back here, what this is really telling us is more people. There are more people here than there are here. Okay? All right, and we look at this, and we're going to look at our yellow line, because these are reported cases, and yeah, it's a little late, the 23rd being the last date that they really have, because it takes a while for data to get to somebody. So by the time you're looking at it, if you go to the site, it will look a little bit different. But let's look at the yellow line, which we can see is starting to form an approximate normal distribution. Do we have this part? Not yet, right? We're right up here, maybe at the mean, right around the mean, maybe we're a little bit past the mean, right? So we can use our knowledge to kind of understand about where we are on the normal curve. That kind of lets you know where we need to go. Now, if we go back to our PowerPoint, I'm going to point some things out. Normal distributions and a full graph require the same conditions. So something screwy happened here with the conditions and here with the conditions and stuff like that. So we are assuming when we look at Prince William County and we're talking about and using our knowledge, conditions don't change. So final thoughts here when you're looking at the COVID-19 graph sources and information. Always check your information source for any biases. Everybody's got some biases. Are they necessarily bad? No. Like Hopkins was biased because they want to help you and they want to help you not be sick, so they're going to kind of put out warning signs. Is that necessarily a bad bias? No, but it's why they're going to pick reds over like calming blues, right? Does that mean anything? No, but if you're looking at it and you're going, red, panic. No, don't panic, okay? Always, always, always check your graphs for X's and Y's axis. Always know your scales. If there are no scales, do not even bother to look at it, right? Watch for little math words that they put in there, like total or culminating or cumulative or per, because those are changing what they're talking about and how they're comparing. If I'm talking about the total number of cases, well, total is only going to get bigger. It is an arithmetic sequence. Each number is going to get bigger. There isn't going to necessarily be an end. Can I sum it? Maybe, maybe not. We already talked. We know that. But it's a graph that will only get bigger if I'm using the word total. If I'm using the word active cases, though, I'm talking about how many currently have it, and I'm taking out cases that have already lived, survived, done, and over with, okay? Per is another one. If they're talking per population, per 100,000, then they're doing a comparison and they're trying to take apples to apples and, you know, taking apples and oranges and trying to convert the oranges to apples with their per. And then always use your brain and use your knowledge, okay? What is going on in the world right now is algebra 2. It's your exponential graph. It's your linear graph. It's your logarithmic graph. It's your z-score. It's your normal distribution. It's algebra 2. You have the knowledge. Use your brain. And I bet you will never, ever, ever ask your math teacher, when am I ever going to use this in real life? Because it's kind of scary sometimes when math comes into real life. I get that. Now, if you want to continue this discussion with me, be my guest. If you have a site you want to ask a question on, email, post it on the Teams page. I am more than happy to talk with you about stuff you find and go over it. I just didn't want to overwhelm you, and I don't want you to be terrified over this. I'm hoping that through all this, what I did was gave you some control over the information you're getting, some way of looking at it and understanding it, and feel like you have some control back instead of just being overwhelmed by all this. So that's it for my speech. Good luck on my worksheet. See you next time.